seeing the title of this video, you might have realized that this video is about the security of our devices, the devices like our phones, our laptops that we use in our day-to-day life. These devices perform cryptographic operations and have cryptographic modules that help in performing these cryptographic operations and storing our keys, our data, our passwords, our biometric data securely on the device. These modules are built on standards. Standards are a set of rules that establish a common language and provide a repeatable way of doing things. These standards also help in interoperability and provide set of functionalities. A well-designed standard is implemented and is accepted by a large number of people. In this video, we will be going through one such standard, that is FIPS 140-2. Okay, so now let us begin our discussion with FIPS 140-2. What is this FIPS? FIPS stands for Federal Information Processing Standards. It refers to a series of computer security standards that were developed by United States federal government in line with Federal Information Security Management Act, FISMA. These standards, they are created by NIST, National Institute of Standards and Technology. FIPS 140-2, this specifically focuses on cryptographic modules that are used in protection of sensitive informations in computers and telecommunication systems. These modules, they can be hardware based, software based or hybrid. The main goal is to maintain confidentiality and integrity of information that are protected by these modules. FIPS 140-3 is basically an improved version of FIPS 140-2. Moving on, there are 4 levels of FIPS security that are mentioned in the document. With each level, the security increases. The lowest one being the lowest security, and the highest level of security provides the highest level of security. Let's go through level 1. Level 1 is the lowest level of security in FIPS 140-2. This requires the use of at least one approved cryptographic algorithm or function. This algorithm or function, this is basically approved by FIPS themselves. No specific physical security measures are required beyond the basic production grade components. The examples can be PC encryption boards that are suitable for low security applications with strong physical network and administrative controls. Now moving on to level 2. This builds an additional layer of security on level 1. This adds tamper evident mechanisms. This is basically used for hardware security. The examples can be tamper evident coatings, seals, peak resistant locks, etc. on the physical devices. It also requires role-based authentication for access control. This basically means that the operators need to assume their roles before they access the particular areas of the cryptographic module. These roles allow only the access to the required parts of the module. This operating system that these modules use, this should be EAL2 or higher certified. What is this EAL? It is basically an evaluation assurance level. This is a category of ranking that is assigned to IT products or systems after a common criteria security evaluation is done. Common criteria, or in short, it's also called as CC. Going to level 3 security. This is stronger than level 2. This provides stronger physical as well as software security. This aims to prevent access to cryptographic keys and critical security parameters that are stored inside the modules. These examples can be strong enclosures, tamper detection and response with data zeroization, etc. Data zeroization is basically done when a tamper is detected and unauthorized access is detected, and all the critical data stored inside that module, it's basically erased, which means that data zeroization. Enhanced authentication is also used, which means that identity based mechanisms are used in addition to the already existing role based mechanism. The operators should also provide an identity based authenticity to the device. Separation of ports physically and logically is also mentioned in the document. This prevents the unauthorized access. Here the operating system must be EAL3 or higher certified. Mm, the next, moving on to the level 4 security. This is the highest level of security in FIPS 140-2. This is this is designed to detect and respond to all physical access attempts. This also provides immediate data zeroization upon intrusion, suitable for physically insecure environments, etc. In addition to that, environmental protection is also available in this level. Environmental protection is basically done to guard against security compromises due to extreme temperatures, voltage fluctuations, etc. In some environments that do not have the normal voltage and temperatures, this can be useful. Specific features or rigorous testing, etc. are also included here in level 4. We will go through all of this in detail in the upcoming slides. The document specifies the security requirements for FIPS 140-2 rating. These include cryptographic module specification, cryptographic module ports and interfaces, roles, services and authentication, finite state models, the physical security, operational environments, cryptographic key management, EMI and EMCs, self tests, design assurance, mitigation and other mitigation of other attacks, etc. We'll go through all of these in the upcoming slides. This is the table of FIPS 140-2 standard summarization. This contains the entire summarization of FIPS 140-2 standard. This is available in the publication and also in the resource of this video. Assuming that this screenshot is not visible in the video, we'll move on to the next slides. The first requirement, cryptographic module specification. Let's break this down. A cryptographic module can be a hardware, software, firmware, or combination of both. It performs the cryptographic functions like encryption, decryption, and additionally it can also perform generation of keys. It must have a defined boundary. It must use at least one approved cryptographic algorithm in an approved mode. This is approved by FIPS themselves. The cryptographic boundary basically specifies that clear boundaries must be mentioned for and also physical limits of the module, and it should not be mixed with the rest of the hardware. For software or firmware, it should include processors and components that are storing the code. This also specifies the documentation requirements. Each step in FIPS, this requires you to create a document in a specified way. The document, how it should be specified for this part is, it should have the software, firmware and hardware and their boundaries that need to be described in the documentation. It should describe the physical configuration of the module. It should explain why the components are excluded from security requirements, etc. It should have a detail of the ports used, logical interfaces, and all the data paths that are used inside this particular cryptographic module. It should also specify the manual controls, status indicators, etc., and relevant characteristics. It must list all the cryptographic functions that are used, etc., and how keys are generated. The authentication data, critical security parameters must also be included. This should also list if non-approved or approved cryptographic functions are being used. Now moving on to the security levels. In level 1 and 2, the documentation may specify an approved mode is being used, and a non-approved mode can also be used in level 1 or 2. The level 3 and 4, the module must indicate when approved mode is activated, and it in level 3 and 4 also the approved mode must be used. Moving on to the ports and interfaces. This section details the requirements of how cryptographic module interacts with the outside world. All the data and physical access must go through a defined port and interfaces. The interfaces can be logical or physical ports. The multiple interfaces can share a single physical port. This must be this can be separated logically though. The cryptographic module must have four logical interfaces. The data input interface, this is used for all the data entering the module like plain text data, key data, etc. It must have a data output for all the data that is leaving the module. For example, ciphertexts, keys, etc. It must have a well defined interfaces. There should be a control input for the commands and the controls to operate the module. There should be a status output for status indicators of the output signals. They should be separate logical interfaces for all of these. In addition to this, there can be separate power port that is required unless the power is coming from the module itself, inside the module itself. The module must distinguish between the data and the control signals, and the data and the status information. The data paths are separate. The data paths must be separated and must not merge with the existing data paths. The output path is disconnected during key generation, manual key entry, or key erasing or key zeroization, basically, which will prevent the data from leaking during the key generation, etc. To prevent accidental leakage, we should also employ sensitive information. We should also employ sensitive information protection. There are independent actions that are mentioned inside the document that are required to perform for such data output. Moving on to the levels of this particular part. Level 1 and 2, the ports and interfaces for the plaintext keys and also the key components, the authentication data, critical security parameters, etc. can be shared with other ports and interfaces, which means that they can stay inside the cryptographic module. They can be shared within the cryptographic module to other ports through other ports and interfaces. In 3 and 4, it specifies that the ports of the plaintext keys, key components, authentication data, and critical security parameters must be physically separate from the other ports, which means that they cannot mix up with physically or logically with other ports. The logical interface for this data must be logically separate from other interfaces using trusted path. The plaintext keys, key components, authentication data, critical security parameters must be directly entered into the module using a trusted path or dedicated cable that is particularly used only for this application. Moving on, roles, services, and authentication. This section defines roles for operators interacting with the cryptographic module and how these roles are authenticated. A module supports authorized roles for operations with corresponding services. The operator can have multiple roles. Depending upon the operator, he can have multiple or single roles. This part also specifies about these roles. There are some authorized roles that are mentioned here, as you can see. The first one is user role. This performs general security services like encryption and other approved functions. This is basically the normal user that is using this cryptographic module. The crypto officer role. This role manages the cryptographic functions like initialization, key input, output, audits, key generation, etc. We'll go through audits later on. Now we'll see what is maintenance role. This is an optional role. This performs the physical and logical maintenance, example diagnostics, and also requires key zeroization whenever the maintenance role is entered or exited. Additional roles or sub roles may be supported, and the document has specified a few of them too. Services. Services are the actions that a module can perform. Each service has an input data that is inputted for that particular service. These data can be control signals, etc. And it also has an output. The output can be data, status information, etc. Every service input should result in a particular service output. This also specifies the required services. The services can be showing status, so meaning that showing the current state of the module, perform self tests, initiates and runs self tests as specified elsewhere in this standard, which I'll be going through in the next part. This also performs approved security functions, like executes at least one approved cryptographic function in an approved mode. Now moving on to the authentication mechanisms. Authentication, this basically verifies an operator's identity and role to access the module and performs the specific services. This helps securing the module from unauthorized access and compromising of critical service parameters. The authentication can be role based or identity based, as we previously discussed. The role based authentication authenticates the selected role or set of roles without the necessarily identifying the individual operator, meaning that it does not necessarily require the identity based authentication. Now, identity based authentication here, it authenticates both the operator's identity as well as the authorization of the selected role. Means the operator, he needs also the role to be selected and also his identity. Now the the authentication strength is also mentioned in the document. The authentication must be strong enough to resist random attempts or false acceptances. The strength, it must be so strong that there must be less than 1 in 1 million chance of success per attempt, or less than 1 in 1 lakh chance of success per multiple attempts within 1 minute. The documentation requirements are also specified. It specifies the supported authentication. We must document the and specify supported authentication mechanism, list the types of authentication data required, such as passwords, tokens, biometric data, etc. It explains the methods for initial access and authentication mechanism setups. It must detail the strengths of supported authentication mechanisms. And also going back to the services, inside the documentation, it must specify all the services offered by the module. For each service, it must have the details of inputs, outputs, authorized roles for performing it, etc. It must specify any service that does not require a role and explain how that doesn't affect the security of the module. Moving on to finite state models. A finite state module is a way to represent the system's behavior as a series of states and the transition between them. It helps to visualize how a module reacts to different inputs and changes the state accordingly. I won't be going through the details of what a finite state module is, as this is a very vast topic. I will only explain the basic idea. Where a finite state module has states and inputs. Whenever a particular input is provided, the module changes its state and performs a particular task. This is also used in compiler designs, etc. The finite state module in FIPS 140-2, this defines the cryptographic module's operations, and this also must be documented along with the finite state module diagram, state transition diagram, table, etc. The finite state module must include all the operations and all the states, including the error states, power on, user mode state, etc. The transition between the states that are triggered by a specific events. These events are basically inputs provided. The input events that cause the transition must also be specified inside the documentation, including the power example the power on, user commands, etc. The output events that are resulting from the transitions, they must also be specified inside the documentation. The states that are used in this particular finite state module are power on off state. This state represents basically if the power is being applied or not. This may distinguish the primary or the backup power. The crypto officer state, the state that manages the cryptography, example initialization, key management, etc. The key entry state or CSP state, the CSP entry state, the states that is entering the cryptographic keys or critical security parameters that are being entered. The user state, the state that is authorized the users to access the security services and also the perform the cryptographic operations or use the other functions. The self test states must also be mentioned, meaning the states that are running self tests on the module. We'll be going through this self tests in the next part of this video. The error states must also be mentioned. The errors can be hard errors, soft errors, etc. Hard errors are basically the equipment malfunctions that require maintenance or repair. Soft errors are software based errors that require reset, etc. Initialization, reset, etc. And here it also mentions that recovery from soft errors is mandatory. This is one example of a finite state machine. Here you can see that from one of the states it enters here, and here now the state is power off, and when power switch on is applied, you can see that it goes to the state of power on. Now next input is provided of begin boot, and it starts booting and it enters the post state. And here you can see that self test pass module configured, this input is provided, and here it goes to no authentication, etc. And you can go through this diagram as an example. Moving on to the physical security section, this details the physical security requirement of cryptographic modules as mandated by FIPS 140-2. Now here we can ask a question, why physical security is important. Physical security, this basically protects the cryptographic modules from unauthorized access like tampering or modification. This ensures that the confidentiality and integrity of the sensitive data like keys and critical security parameters are maintained even when a malicious actor has access to the physical access to the device. Now we have different types of physical modules that are mentioned in the document. The first one is single chip cryptographic module. These are the simplest form of modules. They have one single integrated circuit chip. They can function as a standalone device, or they can be embedded with a larger enclosure, or they can be used as a product that may not have its own physical protections. These basically do not have any multiple modules. They are only a single chip module and single chip controller. The examples are like smart cards, the single chip controllers, etc. Multiple chip embedded cryptographic modules. These modules contain multiple IC chips that are interconnected with each other, and they are housed within an enclosure, or they are housed within a product that may not be physically protected themselves. They are separated, these ICs are separated from one another, and they have their separate casings. The common examples include the adapter cards, the expansion boards that add additional cryptographic capabilities, etc. The multiple chip standalone cryptographic module. This is basically multiple chip cryptographic module, just that all the ICs are included in one casing. They have a dedicated enclosure that is designed to be physically tamper resistant. These modules are typically used in security critical applications where the high level of physical security is necessary. The examples can include the encrypting routers, secure network appliances, and dedicated cryptographic devices, etc. Moving on to the security levels and requirements. In level 1, a basic protection using the production grade components and enclosures is enough. Moving on to the level 2, tamper evident mechanisms like seals, coatings, or the enclosures are required. In level 3, strong enclosures with tamper detection and response mechanisms should also be implemented. There can be removable covers and doors that are also mentioned as mandatory in the document. The automatic zeroization must also be included whenever maintenance access is done. Whenever a person or the device undergoes maintenance, the zeroization must automatically done. Zeroization meaning the erasing of all the critical security parameters and keys. In security level 4, this is the strongest level. This mandates the tamper detection envelopes, strong enclosures with response mechanisms for the entire enclosure, and the environmental failure protection and testings. What are these environmental failure protection and testing? We'll go through in the further part of the video. This table goes through all the requirements for the cryptographic modules. Going through the general physical security requirement, at level 1, production grade components are enough and no additional mechanism is required. Going through level 2, tamper evident mechanisms are required that include the covers, enclosures, or physical seals that are used for physical protection. At level 3, the automatic zeroization, whenever accessing the maintenance access interface, tamper response and zeroization circuitry must be present, and there should also be presence of protected vents, meaning that if a module has a maintenance role that is required a physical access or allows a physical access for an authorized individual, for example a vendor, a maintenance access interface must be defined. This interface encompasses all the physical access paths, including the removable covers or doors. Any removable covers or doors within the interface must be secured using an appropriate physical security mechanism. All the plain text, secret and private keys and critical security parameters, they must be zeroized when the maintenance access interface is accessed. The documentation must contain the details of all the implementations of these mechanisms. At level 4, EFP or EFT mechanisms for temperature and voltage resistance must be included, which will be discussed in the next slide. Now going on to the single chip mechanism. At level 1, no additional security measures are required. At level 2, tamper evident mechanisms are mandatory. This can be covering the tamper evident coating, etc. At level 3, a stronger tamper evident mechanisms are required. The module can be covered with a hard opaque tamper evident coating. Example of this can be epoxy, which makes the internal implementation invisible. Alternatively, the enclosure itself can be designed such that any attempt to remove or penetrate it will likely damage the module beyond its functionality. At level 4, it is the most strong physical security level. The module must have a hard opaque coating which is difficult to remove without damaging the module. This coating should also be resistant to the solvents that can dissolve it without harming the module itself. Now going on to multi-chip embedded modules. These at security level 1, if the module is housed within enclosure or has a removable cover, these components must be production grade. At level 2, the multiple approaches are applied here. The component can be covered with a tamper evident coating or plotting material that is resistant to etching or tampering attempts, etc. The module can be encased in a tamper evident enclosure that that basically does not allow any unauthorized access and provides an evidence for tampering. At security level 3, there are several options. Even here, the entire circuitry can be covered within the hard opaque plotting material, or the module can adhere the stricter physical security requirements defined for security level 3 in the section for multi-chip standalone cryptographic modules also. In the level 4, the most strong physical security measures are mandated. The module components must be covered with plotting material or housed within the enclosures, tamper evident envelopes, etc. The envelope can be flexible circuit, or it can have a special pattern of conductors and which is non-flexible brittle circuit designed to detect tampering attempts. The multiple chip standalone system at level 1, this basically is the same as the previous one, but it has a hard plastic production grade enclosure which may have doors or removable covers, and no additional security features are required. Like the similar one, this enclosure can also be opaque to prevent visual inspection, etc. Any doors or removable covers with on the enclosure, they need to be secured with pick resistant mechanisms or tamper evident seals, etc. mm, the At level 3, the internal security can be the internal circuitry can be covered with hard opaque plotting material, etc. The material is typically epoxy resin or other compounds that are used uh, for the for the circuit boards, etc., for solidifying and form it into a solid mass that basically covers all the internal circuitry and makes it invisible. Additionally, the plotting material can provide some extra environmental protection from moisture, dust, vibrations, etc. The module can be housed with a strong enclosure that is designed to be highly resistant to be removed or penetration, likely damaging the module if someone tries to attempt any such ways. It must also include tamper detection, response, and also the zeroization of the circuitry, like in the previous module. Moving on to environment failure protection and environment failure testing, there are different requirements at different levels. The security levels 1, 2, and 3 of the modules, they do not require the EFP or EFT, but the security level 4 mandates the use of EFP or EFTs, as we saw in the previous slide. Now going through what is EFP. EFP, this feature safeguards the module against any abnormal environment conditions that are accidental or that are deliberate. That they fall outside the normal operating range of the module. The module continuously monitors the temperature and voltage. Upon detecting such conditions, the EFP circuitry takes the action, like shutting down the module to prevent further operations, or immediately zeroizing all the security sensitive keys and critical security parameters. The documentation must include the operating temperatures, voltages, etc., and also specify the features implemented in the module in such cases. The environment failure testing, this basically includes the testing of the modules in conditions that are outside the normal operating conditions. The temperature testing must also cover a wide range of testing, like negative 100 degree or positive 200 degree Celsius, etc. The voltage testing covers a range from minimum negative voltage to minimum positive voltage, causing the zeroization, including the conditions such as polarity reversal too. The documentation must also include the informations that specify these technologies that are used here, and also how the module is resistant to the voltage and temperatures. Let's go through operational environments now. This operational environment refers to the management of software, firmware, or hardware components that are necessary for the cryptographic module to function. This consists of the context in which the module operates. This includes the system it interacts with and also the processors it runs. There are several types of operational environments mentioned in this document. The first one is non-modifiable environment. This is basically inside this environment, certain components are fixed and cannot be altered. Example, the firmwares that are stored inside the ROM, read-only memory. The software executed on a computer with input and output devices is disabled here. The second one is modifiable environment. Inside the modifiable environment, the components can be reconfigured or modified here. The firmware stored inside the RAM is one of the examples. The software executed inside a general purpose computer is one of the example here. The limited environment. A limited environment is a static and a non-modifiable virtual setup. The example for this is a Java virtual machine running inside a non-programmable PC card. The general purpose environment is basically a environment that uses commercially available operating systems that manages softwares, firmware, processors, etc. Example can be word processor. The different levels of security mentioned in this context are: at level 1 security, a single operator mode must be present, which means that only one user at a time can operate the module. This prevents the concurrent access to the module. There should be key and data protection. This means that the module isolates the cryptographic keys and critical security parameters and other types of secret information and values from from other processors while running. The software and firmware protection. This basically defines the cryptographic software and firmware must be protected against any unauthorized disclosure and modification of the data. Integrity checkup is an mechanism like MAC or digital signature that can be used to verify the integrity of the cryptographic software and the firmware components. This must also be included at level 1 itself. Now at level 2, the mechanisms that can be included are trusted operating systems. The operating systems must meet the functional requirements that are specified in another document, that is Annex B, which I'll be showing you at the end of this video. This must also pass the EAL2 evaluation or equivalent trust platform. This must also include discretionary access control DAC. This means that the OS access control mechanism must be configured to define roles that are allowed to execute the cryptographic software or firmware. It should also define the roles that are allowed to modify the cryptographic components, example keys, critical security parameters, etc. And it should also define the roles that are used to read these data and also enter the keys and critical security parameters inside the module. Process protection basically means the OS must prevent the operators or the processors from modifying or um, executing any cryptographic processes which are unauthorized. Auditing is basically making record of the modifications, access, deletions and additions of the cryptographic data that were being made. The attempts of invalid crypto officer function must also be made note of. The operator addition, removals, etc. must also be recorded. Uh, and some additional audits can also be performed that are mentioned inside the document. At level 3, the OS is even more trusted with EAL 3 certification or above. This requires an informal security policy module etc. to be evaluated, that is mentioned inside the document, which I won't be going through the details of. The trusted communication must be established. All the cryptographic keys, secure parameters, authentication data, all should be communicated within a trusted mechanism like dedicated ports, trusted paths, etc. The trusted path details are also specified, like if the trusted path is used, the system must support a secure connection between the module and the operator whenever required, and this path must not be always open, which might lead to vulnerability. The communication initiated exclusively by the operator for the module for this particular purpose must be isolated from any other paths. The next point is enhanced auditing. Enhanced auditing basically adds some extra features to the auditing that we discussed in the previous part. Here, in addition to the previous auditing, it also attempts to use the trusted path function and also the identification of trusted path initiator and the target that has accessed this. At level 4, the OS is basically high assurance OS. Here, the operating system must meet the functional requirements that are specified in the other document, and also it must be evaluated at EAL 4 or above, and rest all points are similar to the previous security levels. Moving on to the cryptographic key management. This section it basically dives into the requirement of requirement of managing the cryptographic keys and key components and critical security parameters throughout their life cycle within the cryptographic module. The cryptographic module can leverage other modules key cryptographic mechanisms as it mentions here, and encrypted keys, critical security parameters using the non-approved algorithms are considered to be plain text. This means that only approved algorithms must be used for the critical security parameters or the encrypted keys to be considered in this particular standard. A strict protection is mandated for security keys, private keys and critical security parameters against unauthorized access and modification and substitution. This the key management scope specifies various things. This also includes the random number generator and the types of random number generators that can be used, key establishment schemes, key distribution schemes, key entry and output, key storage, key zeroization. All these are mentioned here. Mm, sorry. Random number generators. Going through this part, we'll go through random number generators. Now, random number generators are optional. If they are used inside the cryptographic module, they must meet these specific requirements that are mentioned inside the document. Both approved and non-approved random number generators are allowed, but the random number generators have certain limitations they must uh, that they must comply with. These limitations are: the output from the random number generators must pass a continuous random number generator test that is specified inside the document. The approved random number generators require an additional testing of the cryptographic module or cryptographic algorithm. The non-approved random number generators for classified applications can be used for key generation or seeding. Um, the commercially available non-deterministic random number generators can be used to generate seeds for approved deterministic random number generators, but they must comply with the applicable random number generator requirements. Now, the random number generator requirements is a separate document that specifies everything about these random number generators and also the cryptographic algorithms and all that we will see at the end of this video. Now let's go through electromagnetic interference or electromagnetic compatibility. Electromagnetic interference is basically when the device or the module, while performing operations, it outputs a few electromagnetic waves which can interfere with the operation of the other parts of the device or the other parts of the module itself. This here specifies the security level requirements of this electromagnetic interference or electromagnetic compatibility. The module must comply with the FCC 47 code of federal regulations, Part 15 Subpart B of unintentional radiators and digital devices Class A. The level 3 and 4, they must comply with the Class B, which is for home use, and Class A, this is for the business use. Now, what is this FCC? Is basically it is a federal communications commission that governs and regulates various aspects of communications within United States. The the particular thing that is mentioned here, that is Title 47 CFR Part 15, is essentially the section. It addresses the unlicensed transmissions, which include Wi-Fi routers, Bluetooth devices, and other low-power communication equipments that are present. I won't be going through the extreme details of this. Going to the part of self-test, there are basically two types of self-test that can be performed. Uh, this section deals with the self-tests that are required for the cryptographic modules as mandated by FIPs. The purpose of self-test is to verify the cryptographic modules proper functioning. There are uh, several types of self-test. They can be power of self-test and conditional self-test. In addition to the self-test, the module can perform other self-tests that are not mentioned here and that are also not mandatory. The power of self-test is automatically performed whenever a module is powered up, and conditional self-test is performed specific whenever a specific function or a specific task is done. Upon failing the self-test, the module enters an error state. The error state, no cryptographic operations are allowed here. The data output is inhibited. or terminated, an error indicator is displayed via the status output interface. Going through the power up tests, the test initialization and output, the power up tests runs automatically when the module is turned on or powered off, reset or rebooted. On the on this test, no operator intervention is required. The test results are output via the status output interface. The data output is inhibited while the tests are running. This will basically help in securing the critical security parameters and other keys, etc. There are several types of power up tests that include cryptographic algorithm tests, firmware and software integrity test, etc. Going through this one by one. Cryptographic algorithm test, this ensures the functionality of all the cryptographic algorithms that are implemented inside the module. Example, the encryption, decryption, signing, random number generation, all these functionalities are tested here. Here there is a concept called known answer test that is used here. Inside the known answer test, the algorithm basically operates on data with a predetermined correct output that is already known. The calculated output is then compared to the known answer, and a mismatch indicates that the test failure has occurred. For algorithms with variable outputs like digital signature algorithms, a known answer test or a pairwise consistency test specified in this document can be performed. The message digest algorithms require an independent known answer test or one included with the associated cryptographic algorithm test. Example, digital signature standard. If the module has two independent implementations of the same algorithm inside the same module, then the known answer test can be omitted. Going through the software or firmware integrity test, this ensures the integrity of all the validated software and firmware components that are present inside the module. This uses error detection or message authentication codes or similar mechanism like digital signature algorithms for performing this. A mismatch between these calculated parameter and previously generated result that was stored indicates that there is a failure. In addition to this, there is another kind of test known as critical functions test. These test the other security functions critical to the module's security secure operation during the power up. Going through the conditional test, the first one is the pairwise consistency test for public or private keys. This ensures that a proper pairing of the public and private keys is used for encryption and decryption or signing and verification. There are two scenarios that are tested under this category. The public key encrypts, and if the if after encrypting with the public key the private key cannot decrypt it, this basically indicates a failure and a wrong public key is generated. And in another case, the private key is used similarly to generate the ciphertext. I won't be going through the extreme details of this. Similarly, digital signature algorithms are also being tested. The software or firmware, going through the next part, the software or firmware load test. This verifies the integrity of the software or the firmware loaded externally into the module. It only applies to validate the software or firmware components. This can use the HMAC algorithms or the message authentication codes. Um, the calculated result is then compared to the previously generated result. And then comes the manual key entry test. Here the integrity can be ensured by manually entering few parameters or the cryptographic key components. Here also some additional methods are allowed, like error detecting codes and uh, other similar mechanisms, etc. Random number generation test is also performed. Here this applies for both approved and non-approved random number generators that are operating inside the modules. The things that are evaluated here are: the first generated block of the bit um, first is saved for comparison, and each subsequent block is compared to the previously saved block. And if the two compared blocks are identical, then the test failure is triggered. There are other types of mechanisms too that are implemented here that I won't be going through the details of. There is also another test called the bypass test. This applies to the modules with bypass compatibility, which allows the module to provide certain services without the cryptographic processing. This is in the low security devices. This might be useful for performance reasons too, or for compatibility with legacy systems that don't support the cryptography. However, the tests are also performed here for the modules. Let's now go through design assurance. Design assurance, this is basically the critical concept inside FIPS 140-2, focusing on the best practices throughout the cryptographic modules life cycle, from the design to the operation. It ensures that the model is properly tested, configured securely, delivered securely, installed correctly, and developed according to the secure practices, accompanied by proper user guidance and documentation. The key areas of the design assurance are mentioned here. Firstly, configuration management. System tracks all the versions of the module, components, and the documentation. Each version has a unique identification number for control and traceability. Mm, During delivery and operation, the security requirements are specified for secure delivery to the authorized operators. The proper installation and initialization procedures are also mentioned. Um, Document in level 1, the documentation specified secure installation and startup procedure, while as from level 2 to 4, the additional documentation details also provide secure distribution procedures for different module versions. Inside the development phase, it basically focuses on securing the development of the module's functionality. There are different security levels here. In level 1, mapping between the design security policy and the source code is done properly. In level 2, functional specification describing and the module's external ports, interfaces, and their purpose is identified and properly managed. In level 3, a high level language for software and firmware development is used. High level specification languages for hardware components using hardware description language, etc., are also performed at level 3. At level 4, formal model using a rigorous mathematical language to describe the security policy is also done, and security policy is described. Mm, there are several other things that are performed in level 4, like source code annotation with preconditions, and also informal proof that demonstrates the design correspondence with the functional specifications based on the pre or post conditions of the annotations, etc. Now, inside Appendix B of the document, you can also find the recommendations that are provided for the software development. Uh, this includes the software development practices that can be used for analysis and reducing design errors. In the last part, we'll go through the mitigation of a few attacks. These are hardware based attacks basically. The first one being power analysis attack. In power analysis attack, basically the attacker tries to find few security or secret parameters based on the power being consumed by the device. This part explores the module's power consumption patterns to potentially reveal the cryptographic keys, etc. More susceptible modules, those using the external power sources, are the more susceptible modules. To mitigate this type of attack, capacitors can be used to level the power consumption, and internal power sources can also be implemented. Manipulating cryptographic operations can also help to reduce the power consumption variations. In the second attack, this timing analysis attack, here the attacker tries to analyze the time taken by the module to perform the cryptographic operations, potentially revealing the information about the key. This assumes that the attacker has the knowledge of the module's design. For mitigating this, we can basically manipulate the cryptographic operations to reduce the timing variations that are existent inside the model. Now the next type of attack is fault induction attack. Here the attacker uses an external force such as microwaves, temperature extremes, etc. to introduce errors inside the module operation, potentially revealing the keys. The modules that are limited to physical security, that have limited physical security, are more susceptible to this type of attack. To mitigate these attacks, we can select a proper physical security features inside the module. Tempest, this aims to remotely capture the electromagnetic signals emitted by the module to potentially steal the sensitive data, like maybe keystrokes or displayed messages. For mitigating this, we can basically use shielding components and network cabling to reduce the electromagnetic signal emissions. Here we'll go through the changes that took place in FIPS 140-3 compared to FIPS 140-2. Here some of the notable changes are that the SHA-3 algorithm is now allowed for hashing and hash-based message authentication code. The SHA-1 algorithm is no longer supported from FIPS 140-3. The Diffie-Hellman key sizes must be in this range, and the shorter bit keys are no longer supported. Even elliptic curve keys must be in this following range of 224 to 521 bits. The RSA key sizes must be of 2048 bits or longer. The rest keys are no longer allowed. The triple DES has been removed in FIPS 140-3. Even there are changes in TLS protocol, like older versions of TLS are not allowed. The key exchange and cipher changes also are mentioned here. For DSA algorithm, the end entity certificates are not allowed for client authentication, and other things like few of these algorithms for key exchange are no longer allowed. Now there are also changes in elliptic curve cryptography, like in the previous slide also it's mentioned that the 192 sized elliptic curve cryptography is no longer allowed, and the larger size starting from 224 is allowed. The TLS requirements still apply. You can go through all of this in this slide. I won't be going through them in extreme details. Now going through SecureEnclave and FIPS 140-2. In the previous video of mine, I had went through SecureEnclave mechanism. Now comparing it with this particular FIPS 140-2, we can notice that there are tamper detection mechanisms, like uh, if the hardware is been tampered, then Secure Enclave has the mechanisms that it can detect it. There's cryptographic algorithm validation too. Like mentioned in the previous video, the Secure Enclave uses a tree-based approach for storing the keys, etc. And it stores the hash of each data component that are divided as blocks, and these hashes are also compared each time before the use. If there is any error, then the error flag is raised. There is also a mechanism for secure key management self tests that are performed, and there is also design assurance that secure development practices have been maintained. There's self power up and self test for key components, etc. Now I'll show you a few documents. Now this is basically the FIPS publication for cryptographic module, the requirements for cryptographic modules. Here it specifies all the approved functions that can be used in cryptographic modules. Here you can see that AES is mentioned here. For instance, I'll just open one of this for you, and it mentions the entire details of how the uh, cryptography should be implemented, including the inputs and outputs, how many bytes and how the calculation should be performed, the states and the state array input and output, how the calculations are performed here, etc. And similarly for all the others also, here it's present. And there's this Annex B, which deals with the security requirement for cryptographic modules. Similarly, this also provides the details of all the security approved protection profiles. Annex C, this document is basically for security requirement for cryptographic modules again. This goes with the cryptographic module specification, ports, interfaces, roles, etc. that we discussed in the video. This goes through more details like random number generators that are deterministic and non-deterministic. Going through this, we can see that even the random number generators, they are given in extreme details in this document, that how they should be implemented. I won't be going through all of this in detail because this will make the video very lengthy. Again in Annex D, here it specifies the key establishment techniques that are approved. You can see that digital signature, standard DSS, etc. are mentioned here. Here the TLS layer security, transport layer security TLS protocol that we also saw in the presentation is also mentioned here, and all the other things are mentioned here. Going through this particular tab, we can see that this is the certificate for Apple Secure Enclave. This is particularly for secure key storage cryptographic module. This is for the standard FIPS 140-2. Now Apple is also undergoing testing for FIPS 140-3, and once this testing is done, it can soon be also certified. Here you can see all the tested configuration, that for which device it was tested, and what was the software that was tested, etc. This is iOS 13 running on iPhone 11 Pro Max. Similarly, other details are also mentioned here. With this, I will end my video. Thank you.